Today I would like to explain Bootstrap Emitter follower. At the end of the session, you will be able to understand the working of Bootstrap Emitter follower and know the need of Bootstrap Emitter follower. Right. Bootstrap Emitter follower is the maximum input resistance of a practical Darlington circuit is only 2 megaohms. 2 and the input impedance will be increased, right? And actually the input impedance for the any amplifier is low. In case of Darlington amplifier, that will be increased to 2 mega ohms. Whenever using this Darlington circuit for the impedance matching, the impedance input impedance should be high and the output impedance should be low. This 2 mega ohms is not sufficient. To overcome that drawback, we are going for the Bootstrap Emitter follower. Right. Higher the input resistance cannot be achieved because of the biasing resistors is connected across the emitter terminal, across the input side. This R1 and R2 are connected across this terminal. That's why the input impedance will be low. So this is the actually emitter follower circuit. This will be calling as a Bootstrap emitter follower circuit. Why we are calling as a Bootstrap emitter follower circuit is if any changes is occurred across the voltage changes. Any changes means any voltage changes are occurred across the R3 resistance, the same experience will be at the output also. That same voltage will be changed across the output. That's why it is calling as a bootstrap. And here we are using a emitter follower circuit. It means a common collector configuration. That's why it is calling as a bootstrap emitter follower. We are pulling the input impedance to the output side. That's why it is calling as a bootstrap emitter follower. Right? Actually, without the R3 and capacitance, this will be calling as an emitter follower circuit. Why? Because we are taking the output from the emitter terminal. In the emitter follower, the output voltage, that will be the voltage gain will be less than unity. Unity or less than unity. Only it will be used for current amplification as well as it will be used for impedance matching device. Here R1, R2 and R3 are used biasing resistances. RS is a source resistance. Actually, the internal resistance of a transistor is indicated with Ri, and the combination of R3, R1 and R2 with Ri is indicated with Ri dash. The parallel combination of source resistance, R3 resistance, R1 resistance and R2 resistance and Ri is calling as Ri double dash. Here we are using a capacitor at low impedances, at low frequencies, the impedance will be low. That's why it will be acting as a short circuit. And by using this capacitance, we can block a DC signal. We can block a DC signal. And this R3 resistance is connected to the base resistance as well as a RE resistance. Okay, this will be combination from input to the output. By using a Miller's theorem, we can divide this R3 as RM1 as well as a RM2. The Miller's theorem says that if an impedance Z is connected in between the input and output, will getting gain A. The same gain will be get that Z can be replaced with the Z1 with at input side. The Z1 is equal to Z by 1 minus K. At output side, Z2 is equal to Z into K by K minus 1. Like that, the same principle we are using in the Bootstrap emitter follower. Right? In our case, R3 is the input impedance between the output voltage and the input voltage, and K is the voltage gain, and this K can be replaced with AV. AV is equal to V0 by Vi. The bootstrap circuit with two resolved components of R3 using Miller's theorem is shown as the two resolving components means RM1 and RM2. RM1 is the input side resistance of R3. RM2 is the output side resistance of R3. Equivalent Miller's resistance at R3. So the previous circuit can be redrawn like this. So here we are removing the R3. That R3 is connected as a RM1 and R3 is connected as a RM2. Right? This RM1 is equals to R3 by 1 minus AB and RM2 is equals to R3 into AB by AB minus 1. Okay. Previously we have seen Z by 1 minus B. In the place of Z we are considering R3 resistance. So R3 by 1 minus AB. So right. Since for an emitter follower, if AB approaches unity, then RM2 becomes a extremely large value. AB becomes a unity means it approaches unity means the voltage gain for the common collector will be 1. Maximum will be 1. Suppose you replace that AB value with 1. 1 minus 1 equals to 0. So the RM2 will be goes to the infinity. That will be extremely large value. So suppose we want to finding out the input impedance Ri dash. Ri dash is the combination of Ri is parallel with Rm. This Ri is the internal resistance of a transistor and Rm is equals to Miller's input resistance. So Ri dash is equals to Rm1 in parallel with Rm. And like output side, the effective load on the emitter follower can be written as effective load means load resistance. Previously, we are considering this load resistance is Re. There is no separate RL here. Now, Re is equals to RL, that is the load resistance. Effective load resistance means we are pulling some input voltage, resistance to the output side. That's why it is calling as RL effect. RL effect is Re parallel to R1 parallel to R2 parallel to Rm2. That's why the circuit becomes at the output side is Re parallel to R1, R2, Rm2. This is the Miller's resistance. R1 and 2, R2 are the biasing resistors at the output. So the effective load resistance can be written as Re parallel to R1 parallel to R2. Why? Because Rm2 is extremely high value. That's why you can neglect at the output side. The advantages is increasing the input impedance as well as decreasing the output impedance, and the disadvantage is voltage gain is less than unity. Actually, what is a bootstrap? The input resistance can be increased greatly by a bootstrapping, pulling the input resistance to the output. The next topic is feedback amplifiers. The simple sample short answer questions are: what is meant by bootstrap? What is the use of bootstrap emitter follower? The sample long answer questions are: with neat diagrams and suitable expressions, explain bootstrap emitter follower. Thank you.